Welcome back, Physical Science. This is the third video in the 6.4 section. So we looked at a few examples here dealing with changes in state as well as quantity of heat changes. So just to quickly review here, if something is in the same state, to figure out the energy used, so one of these angled lines where they're going down or up, cooling curve, heating curve, Q equals mc delta T, which represents the quantity of heat equation. But if we're dealing with a change in state, gas to liquid or liquid to gas, depending upon the type of curve, that's where the latent heat equation or the hidden heat, the increase or decrease in potential energy versus in the quantity of heat, the increase in or decrease in kinetic energy. So I left you with these three practice questions, so we'll look at them. So how much thermal energy is released when 2 liters of liquid water freezes? So here we have water freezing. Obviously it's a cooling curve, and we'll be looking at just simply the change in state. So if you sketch the whole graph, we're just dealing with this part, liquid turning into a solid. So it's just going to be one calculation. If we quickly look at the rest of these, how much thermal energy is absorbed when a 350 gram bar of gold melts? So it's absorbing energy, so it's a heating curve. And here we're talking about gold melting. So obviously that's going from solid to liquid phase. So on our heating curve, we're concerned about this one part right here. So it's going to be one calculation as well. The last question, how much thermal energy is released when 500 grams of steam at 100 degrees C condenses into liquid water and then cools to 50 degrees C. So we're looking at steam condensing and then cooling down a bit. So actually we have two sections there. So it's steam, and we're told it's water. So it's at 100, which we know is the boiling point or condensation point. So simply this section and then cooling off. So there's going to be two calculations there as well. So if we take a look at the first one, thermal energy released when 2 liters of liquid water freezes. So we're looking at water freezing. So if we go back, it's the latent heat we're looking at. So for water, vaporization or condensation are the same number. It just depends upon whether we're vaporizing or condensing. Excuse me. So if we're vaporizing, it's 2.3 times 10 to the 6 joules per kilogram, but if we're undergoing condensation, condensing, so it's going to be negative 2.3 times 10 to the 6, I believe that number is. So if we take a look here, I guess I was in the wrong spot here. It's freezing, not condensation. Sorry about that. So freezing water. So here fusion or freezing, it's 3.4 times 10 to the 5 for fusion. Therefore, vice versa for freezing, negative 3.4 times 10 to the 5. So there we go. There's where that number comes from. And again, just to note, thermal energy released, therefore we use the negative sign there. Because it's not undergoing fusion, it's freezing. It's releasing heat, losing heat, so it's negative. And in terms of water here, we had 2 liters, and 2 liters is equivalent to 2 kilograms. Just like 2 grams is 2 mils, the density of water is 1 gram per milliliter, so that is a true statement. So Q equals M times latent heat of fusion, or in this case it's going to be freezing. So quite easily done here. 2 grams times negative 3.4 times 10 to the 5 joules per kilogram, and I get negative 6.8 times 10 to the 5 joules. And of course, yes, we use the negative since energy is being released when water is freezing. Okay, number 2, how much thermal energy is absorbed when the 350 gram bar of gold melts? So gold we're going to have to look up, and melting or fusion, 1.1 times 10 to the, I think that's 5 joules per kilogram. So there we have it, 1.1 times 10 to the 6 joules per kilogram. So that was the number I just simply pulled from here. Gold, 1.1, it's fusion, there we go. And of course it's positive because the gold is absorbing heat in order to melt. So 350 grams it was, so divide by 1,000 to change to kilograms, 0.35 kilograms my latent heat of fusion. So there we go, 0.35 times 1.1 times 10 to the 6, and we get 3.85 times 10 to the 5. Since I have two sig figs here, to keep the 3, keep the 8, that's a 5, so this gets bumped up to a 9. Okay, so 3.9 times 10 to the 5. The last one, steam. So we have it condensing and then cooling off. Condensing and then cooling off. So if I look there, condensing and cooling off, it's 500 grams, so that's 0.5 kgs. We're going to have to find the temperature change for the quantity of heat calculation when it's in this section of the graph. So I was told that, of course, it condenses or boils at 100 degrees C, cools down to 50, so final temperature of 50 minus initial temperature of 100, and I get negative 50 for that temperature change later on here. But first I have to figure out the condensing part. So going back here to the chart, for water, vaporization or condensing, 2.3 times 10 to the 6, since it's condensing, it's going to be negative 2.3 times 10 to the 6. So if we take a look here, negative 2.3 times 10 to the 6, since we're going from gas to liquid, it releases energy, so we have to ensure that that is a negative number. Okay, so two calculations here because two separate areas on the graph. We have the latent heat calculation and the quantity of heat calculation when it's in a liquid form. So just as previously, using the latent heat of vaporization in this manner, except it's condensing really, so I could call it LC, it doesn't matter, but just make sure you have that negative in front. So we have negative 1.15 times 10 to the 6, and yes, we need to have the negative there because energy is released. Similarly over here, the quantity of heat, our mass of water is 0.500 kgs, and if we look back, let's see, I think it's on in my section here, I believe it's on page 12 here, but if you look back to 6.3, you'll find the specific heat capacity for water, 4.18 times 10 to the 3. So that's where we get that number from. So if we go back to here now, so 4.18 times 10 to the 3 joules multiplied by the change in temperature, which I figured out the change in temperature is negative 50. So there we go. We have negative 1.045 times 10 to the 5. So we have the heat, the latent heat, quantity of heat. So the total amount of heat released when going from here to here, we just simply combine both of those. Negative 1.15 times 10 to the 6 joules and my negative 1.045 times 10 to the 5 joules, and we get a total of this. Round it off to 2 sig figs, because I think that's what we have in our original question here. And negative 1.13 times 10 to the 6 joules. Okay? So that is how we do that. So the key thing with these questions, figure out if it's a heating or cooling curve, and then from there, see if you can isolate the section that you need, or sections. In one of the practice problems, I think there's one question involving all 5 sections, if I'm not mistaken. And of course, if it's a change in state, flat line, you're going to be using this, the latent heat equation. Quantity, or sort of the latent heat is equal to mass times the latent heat of fusion or vaporization. And if it's just simply heating or cooling in one particular state, we use the old quantity of heat equation using this specific heat capacity found earlier. Okay, so that's the end of that video. The 4th video will deal with some special properties of water. We'll see you soon.